Today we continue analysis of DC electric circuits, and so far we considered only directed current, which is floating in the same direction with constant magnitude. So now we consider direct current. Again, that's the definition. It flows in the same direction, doesn't change its direction over time, but in this consideration, we will deal with time-dependent magnitude of electric current. So we consider the following electric circuit, which will be our model system for such called transient currents, which change in magnitude over time. So we have some battery with electromotive force epsilon. Then we have a capacitor and a resistor. So here we have a switch which can go in two positions, A and B. Today we will consider position B. So let us assume that at t equals 0, the first moment of time, there is no charge accumulated in the capacitor. So we switch this switcher into position A, and the question is, will we have any current in the circuit or not? So from first point of view, looks like that we don't have any current because there is a dielectric layer in between plates of the capacitor here. So we technically have an open circuit. Its resistance is equal to infinity. If we consider Ohm's law for DC electric circuit, which we considered like introduced last lecture, we will realize that total resistance of the DC circuit will be R plus infinity, and that will be in the denominator. So it will be epsilon divided by infinity, means magnitude of electric current is equal to 0. However, in this particular case, here will be current flowing through the circuit. However, it will be time-dependent current, and its maximum value will be defined by electromotive force and load resistance. However, that is only at t equals 0. As time will pass, electric charge will be built at the plates of the capacitor, and its polarity is in the opposite direction to polarity of electromotive force. So they will start to counterforce each other, and current will rapidly decrease until it reaches 0 when capacitor is fully charged. So fully charged, total charge Q will correspond to capacitance times epsilon. That's the maximum charge which can be accumulated at this capacitor, and in that case, potential difference between plates of the capacitor will be equal to electromotive force. They will compensate each other, and there is no current in the circuit anymore. So we can apply second Kirchhoff's law, like Loop's law, to this electric circuit, this large loop. So it will look like epsilon minus Q over C minus I times R, that is equal to 0. So Q here is magnitude of electric charge accumulated at the plates of the capacitor. And now let us express the current from this equation. It will be I equal epsilon over R minus Q over RC. So what is the other option to express current by definition? That is first derivative of, like if we are talking about instantaneous magnitude of electric current, that can be given as first derivative of electric charge over time. So in other words, it's the rate how electric charge is passing through a cross section of a conductor per unit time. Charge per unit time. So now we substitute this derivative instead of I. Here we get epsilon over R minus Q over RC. What we do next, let us multiply and divide first term here in the right side by C. So it will be epsilon C over RC minus Q over RC. And from here we get the following form. It will be minus Q minus epsilon C over RC, since we have here the same denominator. So now we have a differential equation with separable variables. So we rearrange them. We have dq over q minus epsilon C, and that is equal to minus unity over RC dt. So now, in order to get the information about charge as a function of time, means charge accumulated at the plates of the capacitor, as a function of time, we need to integrate left and right side of this equation. So this will be the following. So integral dq minus epsilon C over q minus epsilon C. This is equal to minus 1 over RC, since these are constants, integral dt. So from here we get natural logarithm q minus C times epsilon, and that is equal minus T over RC plus some constant A. At the moment T equals 0, Q is equal 0, and that is the reason why we have maximum current flowing I maximum equals to epsilon over R. So now let us set these conditions, and what do we have? We have natural logarithm of minus epsilon C, that is equal to A, our constant. So now we know the constant, and we can write natural logarithm Q minus epsilon C. Here will be minus our constant, which is natural logarithm minus epsilon C, and that is equal to minus T over RC. Now, the difference between logarithms gives us logarithm of the ratio. So we can write natural logarithm of q minus c epsilon over minus c epsilon, and that is equal to minus t r times c. Now, how we get rid of the natural logarithm? We use exponential function, yes. So now we can write that q minus c times epsilon over minus c times epsilon. That will be equal to exponent minus t over r times c. Now, with rearranging this, we can get the following. So it will be q as a function of time will be equal to c times epsilon minus c times epsilon times exponent minus t over rc. And this is equal to c epsilon 1 minus exponent minus t over rc. So this is the expression for time-dependent electric charge accumulated in the capacitor. And now, kind of our goal was to get the expression for electric current as a function of time. So any suggestions how we do that? We take the first derivative over this function, of this function over time. So electric current as a function of time is equal to dq over dt. So here we will get first this c times epsilon, and this unity will give us the 0. Then we will have minus c epsilon times exponent minus t over rc and times minus 1 over rc. So we take first derivative of exponent, that is the same, and then we need to take the derivative multiplied by derivative of the argument of this exponent. So eventually, what we get, we cancel this c, and also this minus and minus cancel each other. So we get epsilon over r times exponent minus t over rc. So this is the expression for time-dependent current. So now, for instance, since we already discussed this before, we see that indeed at t equals 0, this exponent will give us unity. The current reaches its maximum value, which is epsilon over load resistance. And if we consider time growing from 0 to some values, this current exponentially means quite rapidly. Exponential function is extremely strong. It will very rapidly decay because electric charge will be accumulated at the plates of the capacitor, and that will result in creation of potential difference at this between these plates of the capacitor, which will counterforce the potential difference at the electrodes of the battery with its electromotive force. So this product here of resistance and capacitance actually is a very important parameter. So RC product, that is tau, which is characteristic time of a RC electric circuit. When it provides us some information how fast we can charge or discharge. Later we will also discuss discharging of a capacitor as this process as a function of time when resistance and capacitance are given. So the larger capacitance, if we, let's say, if we keep constant resistance, increased capacitance means we have capabilities to accumulate more electric charges in this capacitor. And as the resistor is fixed, the magnitude of electric current which can flow through the circuit is limited by this resistor, so it will take longer to charge or discharge this capacitor. In the opposite case, when we fix capacitor and change the magnitude of resistor, we will get the case when for large resistor, it will limit the current, the maximum current. Here you see that maximum current is limited by the load resistor. So it will take longer to charge or discharge a capacitor with given fixed capacitance. So that's why the product of these two actually gives us this characteristic time, which defines the response time of this system, capacitor and resistor. So if we consider, for instance, what it actually means, so we can take a look here on this expression for current. I is equal to epsilon over R, which we can substitute with I maximum. And here will be exponent minus T over tau. So instead of RC, we can write tau. So now what is the meaning of this time constant? So that is the time interval within which the current will decrease from maximum value by E times, which E is Euler's number. E is equal to 2.780. And in other way, we can write that it will be equal to 0.368 I maximum. So that is the definition for tau characteristic time, what it means. So when you decrease this time interval which takes for the current to drop from its maximum value to the value which is equal to E times smaller than maximum value. And also we can introduce it in from the point of view of electric charge, because you see electric charge as a function of time also has this RC product in the denominator of the exponential argument. So we can write that over this time interval at tau, the electric charge will reach 1 over 1 minus E in the minus first power, and that is equal 0.632 C epsilon. So it will reach like 63% of the maximum charge which can be accumulated in the capacitor. So these are two ways how you can define the nature and meaning, physical meaning of this time constant tau. So if we consider, for instance, units for this parameter tau, so that is units for resistance times capacitance. So how do we define resistance? That is potential difference divided by current, delta V over current. Then, so that stands for resistance. How do we define capacitance? That is charge divided by potential difference. So what we have here, we cancel out this potential difference. So we have charge and current in the denominator. How we can represent current? It's charge over time interval. So we can write here Q over I divided by, over Q divided by delta T. So Q and Q we cancel out, and eventually we get time interval delta T, which is the dimension of time. Or in terms of units, we measure them in seconds. Now let us show graphically the dependence of electric charge and electric current versus time. So we have Q as a function of time. Here we can show the maximum charge which can be accumulated, so C times epsilon. And this is how our function looks like. So it increases over time, approaches this maximum charge which can be accumulated at the capacitor, and at some time interval which is tau, and that is equal to R times C, we will have this like 63% of maximum electric charge accumulated at the capacitor. So it will be 0.632 times C epsilon. So this is about charge. And if we consider electric current, here, I as a function of time, we will start from some maximum current, which is epsilon over R. That will be our exponential decay of electric current, which eventually approaches to zero. So here is our zero. And at some time interval tau, which is equal to R times C, we will get remaining only like about 37%, 0.368 of initial maximum current, which is, we can replace it, 8. Here it will be epsilon over R. So that is the graphical representation of those equations which we derive for time-dependent electric charge at the plates of the capacitor from t equals 0, and also how electric current magnitude will change in the electric circuit as a function of time. Keep in mind, we see here change only in the magnitude. It rapidly changes, but direction of this current always remains the same. So it flows in one direction. So that's why, regardless the fact that current is a strong function of time, we still describe it as a DC current. So let us summarize our discussion for today. We introduced a special electric circuit, DC electric circuit, where we can realize transient processes of charging a capacitor when it's connected via load resistor to some battery, and investigate the flow of DC time-dependent current through this circuit. So in the moment when we have discharge capacitor connected via load resistor to the battery, when we turn on this circuit, like short it, with a switcher, we start to charge capacitor with the maximum current, which is limited by two parameters: epsilon with the electromotive force and load resistance. Once this charge is floating and results in the charging of the capacitor, this accumulated charge at the plates of the capacitor will create potential difference at the plates of the capacitor. This will be directed in opposite to the electromotive force and slow down the electric current in the circuit until it goes to some a minimum value equal to 0. So then we have equal potential difference at the battery and at the plates of the capacitor. Then capacitor can be considered as just open circuit with infinity large resistance. So this is pretty much everything for today. We will continue to discuss these transient processes in RC electric circuits next time, and that will be the moment when we switch the switcher to another position B, if you remember, we had that, and then we already start at t equals 0 with charge capacitor, and we'll see how charge capacitor will discharge over a load resistor. And obviously that will be as a function of time. Thank you very much for your attention. See you next time. Have a good evening.